Hello and welcome to my presentation on secure storage in Opti. I'm Jens Wiklander, Linaro Security Working Group. The last release of Opti, we have some significant updates in secure storage, so it was time to make another report to bring people up to date. So I start with the agenda is what is secure storage, just a recap from previous sessions, and the timeline on when we have introduced the different features. Encryption keys, that scheme isn't really changed, but it's important, so I will do a recap on that. And then we have the new way of dealing with secure objects, and the anti-rollback that we use RPMB for. So, what is secure storage? It's where we store objects and keys for a TA, and it should be only accessible for that particular TA, and no one else should be able to manipulate with the objects or even see what's in them. Preferably not be able to tell very much at all about the objects. And then since Opti is we are working with the global platform APIs, so we support all the ordinary global platform APIs used for manipulating secure objects. And as we can see here, we have improved secure storage over time. Last presentation, I think, was at 2.1 with the multiple storage support. After that, we have improved isolation between TAs and simplified parts of the implementation and then after that, improve the integrity with a hash tree, which I'm going to talk about today. And finally, also use RPMB for anti-rollback protection. So the encryption keys. Each secure object is encrypted with a file encryption key, which is unique for that file. It's when a new file is created, this file is generated. And the file encryption key itself is also stored inside the key and then encrypted with a trusted application storage key, which is unique per application, and it's in its turn derived from the secure storage key, which in its turn is derived from the hardware unique key. So the hash tree, this is where it's starting to get interesting. It's a complete binary tree, meaning that all the higher levels in the tree is full, and we fill from left to right, so there's no gaps. That's always, node 1 to 6. If you have that, you always have a node 5 also. So we have no holes in the sequence of nodes. And each node is used to protect the different blocks that the secure object itself is built up from. I will come to that in later slides. And we use AES GCM as encryption and integrity protection of the content of the files. So we have a tag and an IB that we need to keep track of, and that's what we put in the nodes. And then the parent nodes keep a hash of the children nodes and so on. That's how we scale it. So it means that we don't have to have a fixed number of nodes or anything. It's just the amount of memory that limits us. A curious thing is that we start counting the nodes from 1 and the data blocks from 0. It's because it's easier when traversing the tree if we count like that. But it means also that the node 1 corresponds to block 0, but that's not so hard to keep track of. And then at the beginning on each, now we're talking about how the file looks in the binary format. So at the beginning of each secure object, we have a hash tree header, which contains the encrypted key that I spoke about earlier. I mean, it's the key that is used to decrypt the object in the end, but it's stored in the file, and a counter, which isn't really used for anti-rollback, but it's used if you don't have anti-rollback, then you can find the latest generation of the header at least. And then we have some metadata that holds the entire length of the object, since it's built up from blocks, and the application expects a bit stream. So we need to know how long it's really supposed to be, and also the number of nodes for when checking the integrity. And it's a bit there's a few steps when building a hash tree header, but we have an initialization vector IB, which we initialize from RNG each time we write it again. And if we haven't generated an file encryption key, we do that and encrypt it with the trusted storage key. And then the counter in the meta header is increased to make sure that you see the new block, not the old one. We have authenticated data, which is one of the input parameters for AES GCM algorithm, which is the hash of the first node, and the counter, the encryption key, and IV. There's some redundancy here, but it's to be safe, and also not to change the way we encrypt stuff compared to before. And then the output, let's see. So we feed this into AES GCM to encrypt, and we get a tag and encrypted metadata. The tag is, you can compare it with an HMAC, for instance, except that it's also used together with the encryption. And the encrypted metadata, that is just the same size as the plaintext metadata, just encrypted. And then we assemble the header as with the IV tag, encrypted encryption key, and encrypted metadata, and the counter. And the data blocks are encrypted as before, actually. They are encrypted independent of each other, but each time we encrypt the block again, we generate a new IB from RNG, and P is the plaintext data that we are going to store, and the file encryption key is generated as for the hash header, also in the same way. And the AAD data is slightly different. We have only the file encryption key and IB fed in there. And so what we feed into AES GCM is plaintext and AAD, and out we get a tag, which is stored in the node in this tree I showed earlier, and the encrypted data is stored as a separate block. The IB is also stored in the block, of course, to be able to decrypt in order to support atomic updates, we need to have 2 versions of each block in order to switch between them when updating in case we are interrupted for one or the other reason. And it also means that, yeah, it becomes like a transaction that is atomic. So we have 2 versions, 0 and 1, and and then we have one version which we call the active version, and the other is the inactive version, and that is toggled all the time while updating. So when we write a block again, we will write in the inactive block, and once it's committed and we update, we will toggle this bit, and it will suddenly become the active block instead. So the different parts we need to take care of is the hash tree header, hash tree node, and encrypted data block. Each one of these has 2 versions. And finally, we have the nodes 1, which is the top node, which protects all the nodes below, and those nodes protects the data block. We write that as the last one, and then we can save the hash of that. And once we have done that, then we have effectively also done a transaction. So we have the new data committed, and we are guaranteed to be able to read it again.
Does that mean it has hit the storage media?
It has. And the steps for it to hit storage media is via non-secure world, so we don't have that much control over exactly how it will end up there. So it's quite important that it's small steps we take when we do it. Yeah. And then in addition to that, we have to keep track of all the objects we have, because these objects are just stored as a binary file in normal world file system. And let's say that someone removes it or do whatever with it, it can be hard for us to see it in secure world. So what we have is an additional file where we store, and it's like a database where we store all the objects that we have created, and we identify it with the UUID of the TA and an object identifier. Object identifier is like a file name, but in global platform language instead. And then we have the hash of node 1, which is the one that represents the integrity of the entire secure object. And then we have also a file number that is just a unique number that is used in the normal world file system. So an advantage with this is that normal world can't really see which file this is, which TA it could belong to, etc. So it hides some information there also. That's good. And then the object list database itself is, of course, also stored in normal world as a special file name, dirf.db. It could have been anything, but that's what we have. And with the RPMB available, then we will store the hash of node 1 in this file, of this file in RPMB. So that means that the hash of node 1 in the object list database, that one protects all the objects that we have created ever. And if we can store that in RPMB, then we have guaranteed that it can't be rolled back, since we have that hash. If RPMB isn't available, we will still have at least have a consistent state, so it means that you can't roll back a single file or remove a file or anything like that. So we have at least a consistent history.
But you could replace with a whole set of old files and then it would look okay?
Yes, we could, but yes, that's correct, but it will limit the attack that you can make. So it's slightly better, and also maybe there's another way of keeping track of this counter that could make it harder to do rollback also, because RPMB is maybe not available because it's a bit expensive.
RPMB in turn is relying on
EMMC.
a root of trust in the secure world.
Yes, so when we communicate with RPMB, we have a shared secret, and it's MAC'd messages that we exchange. If we want to protect the content from, so no one else can read it, then we need to encrypt, and that's what we do also in certain places. Sometimes it doesn't matter, so. Yeah. So it means that when we communicate with RPMB, we do it via the Linux kernel, and yeah, it's like a channel we use via normal world. So we have still some stuff left to do in secure storage. How we deal with the RPMB, that we don't program a key unless we are debugging or testing. Otherwise, it's a typical production case. So it should not be done in normally in a product. And then we can improve the derivation of the keys. But so far we don't have any good reference hardware to do that with. It would be nice to have such a feature in Opti to demonstrate that. And then we have these nodes. Like if the file is large, the secure storage file is large, they will eat up quite a lot of memory, so we could handle them in a more efficient way. Maybe only read in, keep those in memory that we really need, and so on, since typically you maybe update one block and then you need only the parent nodes in order to update the hashes. And another thing could be to store trusted applications in secure storage also. That would make it, that will solve the anti-rollback of trusted applications in a nice way. And that's actually something we are working with a bit for the moment. Maybe we'll see it next Connect. Yeah, that was everything. Any further questions? Yes?
Yeah. Your model for secure storage, it doesn't seem to allow for a certain use case that we have a lot, and that is we want to store things like XTS keys, keys stored, disk encryption keys.
So what? Store?
We want to store disk encryption keys.
Yes.
XTS, the XTS. We want to store them securely. And what we want to do though is we want the application, which is not secure, to be able to go and say, give me the wrapped version of this disk encryption key, and I'll pass this to the crypto hardware to decrypt the block. When you pass it to the crypto hardware unwraps it and uses it, and therefore the non-secure application never sees the real key. But I want to be able to store up to like 1 million of these disk encryption keys encrypted on my secure storage and have regular non-secure apps be able to get them, cache them, and send them up. And this architecture seems to say that only secure applications, TA, can actually use the secure storage, not regular.
Yes, that's correct. But you could, on the other hand, a TA can serve a client in normal world. So it could store keys for a client in normal world. But if we are talking about thousands of keys, maybe it doesn't scale well enough, and we could need some other solution. Because in the end, what we do with the secure object is that we store it as ordinary files in the file system. So maybe that's a chicken egg problem also, if the disks are encrypted.
When you store the majority of your files on RPMB, what file system are you using?
You store them in RPMB instead.
But RPMB, I thought RPMB doesn't really have enable a little file system because it uses just sectors, or half the sector is used for authentications and Macs and shit like that. You can't really just read and write with files and stuff.
There are a couple of different kind of storage. They are just outside of the box.
What is the file system?
The RPMB keys are stored with, you access them with a special command and everything.
Right.
It's not a block, it's not even 512 bytes, so it's a different thing altogether. It's outside of the storage of the device.
Because as far as I understand, Linux doesn't have a RPMB file system.
We have an RPMB file system also.
Part of preserved stuff.
Yes, and I had one slide where I mentioned multiple storage, so it means that we have both the normal default storage, which uses a normal world file system, but we also have an RPMB storage that an application can select to use as storage in addition to the other one. So that means that you can create a trusted application that stores your keys in RPMB and can retrieve them from there also. That could be maybe you need, how this application gets into memory if you can't read the file system. That's maybe something to think about, but I'm sure it's possible to do something about that. Other questions?
I guess there's quite a lot we can do with this. I think in the kernel there is something like a PKI, public key infrastructure thing going on somewhere. It would be interesting to make it possible for that subsystem to have a standard TAs to talk to store keys and stuff like that. That would be kind of interesting, but it would have to be engineered.
Yes, and then suddenly there's another T instead that doesn't support this, and
Yeah, but that's just the open platform standard.
Yeah.
They say like T with this UID will serve you with this, and then the kernel will go.
yeah, that could be nice. And
So, like, I think there are like some use cases like that where we like want, I'm a kernel developer, so like we want services from the secure world, like please store our secrets, like we do with the TPM currently.
yes, and you don't need to expose the keys even. You only keep them in secure world. That's good.
Yeah, just like the TPM.
Yeah.
That would be really good. Another question I had is about failover at power failure. It looks like the transactions are kind of atomic.
Yeah.
What about power failure? I mean, it doesn't really, it leaves it to somebody else to keep the integrity of the files stored in the real file system to somebody else. So if the files get corrupted or something like that over there, or locked in the file gets corrupted, I mean,
Then it's
then finito.
yeah.
Yeah, so we really have to be able to trust where your subject counter or whatever, the thing on the other side, where it's storing things that it actually keeps integrity of them.
Yeah,
problem for that data.
that's a normal world. Yeah, it has to do that, or it will. Yeah, you could consider it a denial of service attack or something.
Yeah, there are some things we do that with POSIX programs, like we said, a sync bit or something like that.
Yeah, you can do an explicit sync or whatever. And since we do it in quite separated steps, it shouldn't be hard to get that to keep it working. I mean, it hasn't been complicated so far. So. Yes.
What if two TAs tries to update some secrets at the same time?
You mean concurrent access to? Currently, we don't have that. So all the access to secure storage is serialized, but it's
One TA just wait for the other TA.
yeah for the current operation to finish. So there's only one operation active at a time. But they can have, several TAs can have files opened and in parallel. It's just that when an actual update is done, then that is only done in sequence. Okay, thank you.